So for example, to demonstrate this property,
This is why we don't use IE.
it doesn't have anything else.
One of the reasons.
So here's the function again. I'm gonna write that identity here. And this will all make sense in a bit. So I'm going to pick m and n so that they don't share any factors with one another. So let m equal 5 and n equals 8. So m is 5. Raise it to the phi of 8. I already showed you that the phi of 8 is 4. Right? And then mod it by n, which n is 8. And I get 1. Okay? So 1. Yes. Likewise, just like 1 to the power of k is equal to 1, I can take any number in the exponent here, k, and it's still 1 as the result. So if I go back here, I can take this 4 and multiply it by anything I want. So anyone give me a number?
42.
42. And I still get 1. Okay? So that's one of the identities he came up with, and that's going to become helpful in coming up with an algorithm for this. So here's kind of the breakthrough. Right, so you can multiply anything by k, and I get 1. Notice this equation and this equation. They're actually very, very similar, except on this one, on that one over there, I have a 1, and on this one I have an m. But what I can do to this one over here is multiply both sides by m, so this 1 is an m, and multiply this by m as well, which is the same thing as adding plus 1 up here in the exponent. Right? And then, since they're both equal to m, what we can do is take the exponents and set them equal to each other. So ED is equal to the phi of n times any constant, k, plus 1. So my decryption key is k phi of n plus 1 over e. So this is the relationship between how the two keys are mathematically linked. So basically, if I pick a prime number that's very large, nobody can find what d is, because you can't find phi of n very easily, but I can, because I know how to factor that prime number, because I came up with it. So let's see here. So I guess we can do an example with this. Let's go back to this. So whenever you want to encrypt a message, you're going to have to convert it to binary. So I'm going to try to send the message hello. Right? So let's go here and get some ASCII to binary converter. Alright, so this is my message that I'll try to send out. And to do the math, I'm going to have to make it be in decimal. Alright, so this is the number that I want to send out, 6841708. So what I'm going to do is pick two large prime numbers. So I've already generated them before. They're not that big, but let's see if I can open it up. Alright, so here they are. So I have two prime numbers here, and I need to find out what n is. So I'm going to take these two numbers and multiply them. and I get this. I think that's right. So now I need to find phi of n. So anyone else, when they see this prime number n, they won't be able to find phi of n because they don't know what two prime numbers they came out of. But we know. We can just subtract 1. And this is phi of n. So alright. I'm gonna pick e to just be 3, the same thing that we've always used. And now I need to find out what d is. So d is given by this equation here, k phi of n plus 1 over e. So let's take phi of n plus 1 divided by 2. Okay, so we get some decimal number, but we can see here that it has 2/3. So what I can do is, remember I have this k here, so I can make any multiple of it. So I'll just pick 2 to make the fraction go away. The fraction is 3. 3. Actually, no, hold on. I think I might have 2 should have done it actually. So let me see here. Let me make sure I did the math on this properly. Interesting. That not work? This. I have another example, which numbers that I did earlier, but which one? Okay, so 2 times this. Okay. Okay, so that I think that's correct. So that is the decryption key. 6, 8, 9, 7, 4, 6, 2, 6, 5. So nobody can get d very easily because you can't factor this n to get phi of n, which you need to find d. So now what we'll do is we're going to want to send the message hello. So I think I already converted this to, so I'm going to try to send this message, right? So what I'll do is m to the power of e mod n gives me the ciphertext. So my message, raised to the power of e, which is 3, mod n gives me the ciphertext here. And I'll send this across the internet to my party. I just basically close the lock right there. And to decrypt it, I do c to the power of d mod n to get back down. So c to the power of d mod n. So you can see that these numbers are not 150 digits long. So
I'm sure it'll do it. I'm sure.
ooh, this does not work. Okay. Well, I have another demonstration which works. I take smaller prime numbers. Alright, so I'm gonna pick 53 and 59. So, do this real fast so I'll show you that it actually works. Okay, so 53 and 59, I get 3127. Alright, so phi of n is subtract 1 and multiply. I get 3016. And then what I'll do is I'll calculate d, which is going to be, again, k is going to be 2. So this is phi of n plus 1, k is 2, divided by 3, I get 2011. Right? So I'm going to encrypt this. I'm going to take my message. In this case, I'll make my message be 89. Raise it to the power of e, which is, I didn't write it, but e is 3 again. Because I divided by 3, so e is 3. So yeah, mod n. And I get 1394. So my ciphertext is 1394. If I take my ciphertext, raise it back up to the decryption key now, and mod it by n, I should get back 89, which is what I wanted to send earlier. Okay, 89. So it works. And that basically is what RSA is, and it's used pretty much everywhere. It's probably the most used asymmetric encryption out there. And yeah, there's also DSA, which is also pretty popular. But yeah, any questions? Yeah?
What happens if I buy a quantum computer?
I don't know, they haven't been made yet.
What happens if I buy hair?
Probably being scammed.
Alright, thank you, Alex. Very good.